Okay, so you know how sometimes like you'll see a really interesting science headline, but then you're like, I don't have time to read the whole paper.
Right.
So today, we're going to give you a shortcut to understanding one of those developments that's really kind of a mind bender.
Yeah, it really is.
It's the fact that physicists have created what's called a Schrödinger's cat state.
At a much higher temperature
Right.
than ever before. So
Right.
when we say higher temperature, we're still talking very cold.
Yeah.
But it is a significant jump.
Yeah, absolutely. So this is based on a paper in Science Advances, and it's got some really interesting implications, especially if you're interested in the future of quantum computing.
Absolutely.
So our mission for you, listener, is basically twofold. First, we're going to try to understand what the heck is this Schrödinger's cat thought experiment, and why was it even thought up in the first place? And then why is it so significant that they achieved this at a higher temperature? What does this mean for quantum computing, which is this very practical and fast-moving field?
All right, so we're kind of tackling two big things here.
Yeah.
A very abstract sort of theoretical problem,
Yeah.
and then a very practical technological advance.
Right. Yeah, exactly. So let's start with the cat in the box.
Okay, so the cat in the box,
And this is,
yeah, this famous thought experiment
yeah.
was created by an Austrian physicist named Erwin Schrödinger
Okay.
back in 1935. And it was really a commentary on the problems that Albert Einstein had raised about quantum mechanics.
Okay, so 1935, so that's almost 100 years ago.
Right, yeah, it's very early in the development of quantum mechanics.
So what was going on that what made Schrödinger think of this? I mean, it's such a bizarre thing to think of.
Right, so what was happening back then is that the predominant understanding of quantum mechanics was being put forward by this physicist, Niels Bohr.
Okay,
And he was saying that quantum entities,
like an electron or something.
like an electron, for example,
Yeah.
they don't have definite properties until they're measured.
Okay.
So it's kind of like they exist in this blurry, probabilistic state.
Oh, so kind of like if you flip a coin and it's spinning in the air.
Exactly.
It could be heads or tails.
Right.
But it's not one until it lands and you look at it.
Exactly. That's a great analogy.
Yeah.
So before you measure it, it's in a superposition of both states.
Okay.
And Einstein really didn't like this. He was very uncomfortable with this inherent uncertainty.
Yeah, because Einstein thought of the universe as very like predictable laws and everything.
Right. Predictable clockwork universe.
Yeah.
And he really questioned how the universe knows when a measurement has taken place and when it should force this quantum entity to decide on a state.
Yeah, it's like, who is the observer? Is it us? How does the universe know that we're looking at it?
Right. It's kind of like, are we playing dice with the universe? And Einstein really didn't like that.
So that's where Schrödinger's cat comes in.
That's where the cat comes in.
So what is in this box with this poor hypothetical cat?
Okay, so picture a sealed box.
Okay.
And inside the box is a cat,
A real cat.
a hypothetical cat.
Okay. Hypothetical cat.
And there is a vial of poison,
Okay.
cyanide.
Yeah.
And there's a hammer that can break the vial of poison.
All right.
And there's a Geiger counter which detects radiation.
Mm-hmm.
And then a tiny little piece of radioactive uranium.
Okay, so this is not sounding good for the cat.
No, this is not a good situation for the cat.
Okay.
But the key here is that radioactive decay is random.
Okay.
So there's a chance that this piece of uranium will emit radiation within, let's say, an hour.
Okay.
If that happens, the Geiger counter detects, it triggers the hammer, which breaks the vial, and the cat dies.
Right, got it. So it's like a Rube Goldberg machine?
It's a deadly Rube Goldberg machine for this poor cat.
Yeah, okay.
But here's where the quantum mechanics comes in.
Okay.
So Bohr's interpretation was that this uranium atom, until it is observed, it is in a superposition of both decayed and not decayed.
Okay.
And because the cat's fate is tied to that atom, the cat is also in a superposition
Of being both alive and dead.
of being both alive and dead
At the same time.
at the same time.
And that's why Einstein and Schrödinger thought this was so crazy, right?
Right.
Because it doesn't make sense.
It's absurd.
Yeah, in our world, a cat's either purring or,
Right, or it's not.
you don't have this kind of blurry in-between state.
Right, and that's why I think this thought experiment was so important.
Yeah.
Because it really highlighted this lack of a clear narrative for how quantum mechanics connects to our everyday experience.
Right. Like, how do we get from these weird quantum rules
Right.
to, like, the fact that I can put my coffee cup on the table and it stays there?
Right, exactly.
Why doesn't it just, like, quantum tunnel through the table?
Right. So the cat is not meant to be taken literally.
Mm-hmm.
It's meant to be a paradox.
Right.
To highlight the seeming absurdity
Mm-hmm.
of applying these quantum rules to large, everyday objects.
Okay, so it's more like a philosophical problem
It is a philosophical problem.
than like a prediction about the real world.
Right.
Okay, so how do we go from this thought experiment to actually making this happen in a lab?
Right. So in the 1970s, there's a lot of research in this area called quantum entanglement.
Okay, I've heard of that.
It's very weird.
It's hard to wrap your head around.
Yeah. So essentially, you can link two particles together
Okay.
in a way that their properties are always correlated,
Okay.
no matter how far apart they are.
Okay.
So if you measure one particle
Okay.
and you find its spin is up, let's say,
Mm-hmm.
then instantly, the other particle's spin is down,
Even if they're miles apart.
even if they're on opposite sides of the universe.
That is so weird.
It is very weird.
It sounds like they're communicating faster than light.
Right. It appears that way, but they're not really communicating.
Okay.
They share this fundamental quantum state
Okay.
from the moment they're entangled.
Okay, so they're kind of linked from the beginning.
They're linked from the beginning. And this is really important for quantum computing
Okay, how so?
because it allows for these very fast and powerful calculations.
Okay, so quantum computing is based on entanglement.
Right. And then in 2010, there was this really remarkable experiment where they actually created a real version of Schrödinger's cat.
Okay, no cats were harmed, I hope.
No cats were harmed.
Okay, yeah.
They used a tiny mechanical resonator,
What's that?
kind of like a microscopic tuning fork.
Okay.
And they put it in a superposition where it was both oscillating and not oscillating
Okay, so it was vibrating and not vibrating at the same time?
at the same time.
Wow, that's mind-blowing.
Right. And it showed that this wasn't just limited to tiny particles.
Right.
Even relatively large objects could exhibit these weird quantum states.
Okay, so this is getting closer to a cat.
It's getting closer,
Right. A tuning fork is bigger than an atom.
much bigger.
Oh, okay.
But the key here is that they had to do this at extremely low temperatures.
Okay, because heat would mess it up.
Heat would mess it up.
Yeah.
So very close to absolute zero.
Right, because all that heat's just like random motion and jiggling.
Yeah, it's like trying to write on a piece of paper that's in a hurricane.
Yeah, exactly.
Everything's just shaking around too much.
So this new research, they did it at a higher temperature.
Right. So this is the big news. They managed to create a Schrödinger's cat state at a much higher temperature than before.
So how high are we talking? Like room temperature?
Not quite room temperature,
Okay.
but they did this with a qubit.
So that's the basic unit of a quantum computer.
Right.
Okay.
And they put this qubit inside a microwave resonator and got it to this state at 1.8 Kelvin.
1.8 Kelvin. Okay, so that's still insanely cold.
Yeah, it's still very cool.
Yeah.
But it's about 60 times higher than the ambient temperature in their setup.
Okay, so that's a big jump, relatively speaking.
It's a huge jump.
Yeah.
And one of the authors, Gerhard Kirchmeier, he pointed out that Schrödinger's original cat was warm in his description.
Right. It wasn't a frozen cat.
It wasn't a frozen cat.
Yeah.
So their question was, is it even necessary to start from this super cold state
Right, to see these quantum effects.
to see these quantum effects?
So what does this mean for quantum computers?
Right. So remember, the Schrödinger's cat thought experiment is all about showing how quantum randomness can affect big things.
Right, like a cat.
Like
yeah.
a cat living or dying.
Yeah.
And the fact that we don't see that in everyday life
Right.
shows how different the quantum world is from our classical world.
Yeah, like how does the quantum world become the world that we experience?
Right, that's the big mystery.
Yeah.
And this low temperature requirement for quantum computing has been a big problem.
Yeah.
Because you need these huge, expensive cryostats to keep these qubits cold.
So if you can get it to work at warmer temperatures,
Right.
that would be a huge deal.
It would be enormous
Yeah.
because it would make these things more practical.
Yeah, less energy intensive.
Right, exactly.
Yeah.
Yeah.
Okay, so how did they actually do this? Did they just like heat up a qubit and see what happened?
Not quite. So they used this special setup with the qubit in the microwave resonator.
Okay.
And they were able to very precisely control the interactions in the system. And one of the authors, Thomas Agrinius, said that their colleagues were actually surprised that this worked.
Really?
Yeah,
Yeah.
because usually people think heat destroys quantum effects.
Right, it just scrambles everything up.
Exactly.
Yeah.
But their measurements show that you can still have quantum interference.
Which is a sign of superposition.
Right, at these higher temperatures.
Wow, so maybe one day we'll have quantum computers on our desks.
Maybe not on our desks, but
Yeah.
certainly not needing these gigantic refrigerators.
Yeah, right.
So as Kirchmeier said, it shows that you can use quantum phenomena in less ideal and warmer environments.
Okay, so what is quantum computing? And why does all this matter?
Okay, so quantum computing is using quantum mechanics to do calculations that are impossible for regular computers.
Like way faster.
Way faster.
Yeah.
Way more powerful.
Okay, and this is all based on how subatomic particles behave.
Right.
So instead of bits, they have qubits.
Right.
And a qubit can be both 0 and 1 at the same time.
Right, because of superposition.
Right.
And that allows them to do many calculations at once.
Okay, so that's where the speed comes from.
Right.
But quantum computers are still very new.
Very new.
Right.
They're small, they're difficult to maintain, and they're prone to errors.
But the hope is that they'll eventually be much better than classical computers for certain tasks.
Right, especially for things like simulating molecules for drug discovery.
Oh, yeah, that's super computationally intensive.
Very computationally intensive. Or modeling the climate.
Right.
Or designing new materials.
Okay, so those are some big potential applications.
Huge potential applications.
Yeah.
And they all rely on the fact that qubits can be in a superposition of states.
Right, and they can be entangled.
Right.
So that's where the real power comes from.
Exactly.
Okay, so what are some of the challenges facing quantum computing?
Well, one big challenge is that they're very sensitive to noise and errors.
Right, we talked about that with the temperature.
Right.
Yeah.
So even a tiny bit of heat or light can disrupt a qubit.
And cause it to lose its quantum state.
Right. And that leads to errors in the calculations.
And how do they deal with those errors?
Well, they're developing error correction algorithms,
Okay.
but those are still in their early stages.
And they require a lot of extra qubits.
Right.
So it's not very efficient yet.
Not very efficient.
Okay.
And there's also the challenge of reading out the results of a calculation.
Because if you measure a qubit,
Right.
you destroy its superposition.
Exactly. So you have to be very clever about how you measure them.
Okay. So it's a tricky business.
It's very tricky.
Yeah.
But there's a lot of excitement about the potential
Yeah, it sounds like it.
because it could revolutionize so many fields.
Okay, so we talked about Schrödinger's cat, and we talked about quantum computing.
Right.
So how are they connected?
Well, Schrödinger's cat is a thought experiment that highlights the weirdness of quantum mechanics.
Right, and quantum computing is trying to harness that weirdness
Exactly.
to do useful things.
To do useful things.
And this new research shows that it might be possible to do those things at higher temperatures, which would be a big step towards making quantum computers more practical.
Huge step.
Yeah.
More practical and more accessible.
Yeah. Okay, so let's wrap this up.
Right.
So Schrödinger's cat, it's this thought experiment from almost 100 years ago.
Right.
And it was meant to show how absurd it was to apply quantum mechanics to everyday objects.
Right.
But now we're actually creating those kinds of states in the lab
Right.
with things like qubit.
With things like qubit.
And this new research shows that we might be able to do it at higher temperatures,
Right.
which could lead to more practical quantum computers.
Exactly.
So it's like this thought experiment that was meant to be a reductio ad absurdum
Right.
is now becoming reality.
Right.
And that's really mind-blowing.
It is mind-blowing.
Yeah, so for you, listener, what do you think? What does it mean that we can create these seemingly impossible states?
Right.
Does it change how you think about the nature of reality?
Right.
And what about the future of technology?
Right. What is the future of quantum computing?
Yeah, and how will it affect our lives?
Right. It's a lot to think about.
It is.
It is, but it's very exciting.
It is exciting.
It's a very exciting time to be alive,
Absolutely.
to see these things happening.
Yeah, so keep an eye on this field because it's moving fast.
It's moving very fast.
And who knows what the future holds?
Who knows?
Yeah, thanks for joining us on this deep dive.
Thanks for having me.
It's been a pleasure.
Likewise.
And we'll see you next time.
See you next time.
Guys, see you in another podcast. Don't forget to subscribe to our channel.